This is a recap of learning from Unit 3, Lesson 2. We're going to use these 3 rules in order to identify the domain of a function, and then we'll represent the domain on a number line as well as writing in interval notation. Let's get started with example number 1. Example number 1, you were just watching. If you were here with me, if you were gone, you are taking notes. So f of x equals x 5 divided by the quantity x plus 2. So the first thing I'm going to do is I'm going to look up here and I'm going to look at the second and the third example. And I'm going to ask myself, do I see a radical in this example? I don't. That means I can eliminate the chance of applying Rule 2 or Rule 3. And the only reason I apply Rule 1 is if I see a variable in the denominator, which I do see. So I'm going to take this and I'm going to say this quantity cannot equal 0. I solve algebraically, which is required. I make a simple number line. I demonstrate that I can display the domain visually on a number line, and then I write it in interval notation. We are not including -2. So, if you are in accelerated calculus and you're not in periods 2 or 3, what's confusing about this is you haven't learned about nth roots. So there's a little number here. You're used to just thinking of this as a square root. Well, a square root actually has a hidden number here. It's a 2. So when I look at this, this is a 2. And you're like, how would I know that? Well, think of this. When you say what's the square root of 4, what that means is what 2 numbers multiply to equal 4. It's 2 times 2. That's how we get 2. When you don't see a number here visually, it's a hidden 2. We only apply Rule 2 and Rule 3 if that nth number, so the number right here is even, 2, 4, 6, 8, and so on. If it is odd, 3, 5, 7, and so on, we do not apply Rule 2 or 3. So I'm going to apply Rule 2. Now, why am I choosing Rule 2 instead of Rule 3? Because this radical with an nth root of 2 is not in the denominator. How do I apply it? This quantity has to be greater than or equal to 0. Greater than or equal to 0. Add 1 to both sides. I divide by 3. Do I have to show the work? Yes, you do. So there's 3 parts. Show algebraically how do we get the domain. Graph it out in a number line. Think of this as an arrow. And then we're going to represent it in correct interval notation. We do not include 1/3, and it's everything to the right. What does this even mean? It means we could choose 1, 2, 3, 10, 100. That's all in the shaded region. You could plug in those values and there'd be a corresponding output value. Example number 3, it's a little tricky. So how do you go about assessing what rule you need to apply? Here's how I think of it. Is there any radical? There's no radical within this function, so I can eliminate applying Rule 2 or 3. Rule 1 says we only apply Rule 1 if there's a variable in the denominator. Well, there's no variable in the denominator, so I'm not going to apply Rule 1, 2, or 3, which means there's no restrictions to what you plug in. All real numbers. Here's how we write it on a number line. We include everything. And here's how we write it in interval notation. What does that even mean? It means you can plug in any real number, a -10, a +10. We can plug in anything and there'd be a corresponding output value. In example number 4, the first thing we're going to do is ask ourselves what rule or rules do we apply. We do not see any radicals, so I can eliminate the chance of applying 2 or 3. I'm looking at 1. I do see a variable in the denominator, so I need to apply Rule 1, which means these 2 quantities cannot equal 0. So algebraically, we must show that. Subtract 2, x cannot equal -2, and subtracting 1, x cannot equal -1. On a number line, I come over here, put them in the correct order from least to greatest. It cannot equal these values, but it can be everything else. So I could plug in a -10 and get a corresponding output. I could plug in a -1.5 or a +5, and I could get an output. We're going to go from -infinity all the way up to -2. We do not include it. We're going to go from -2 to -1, not including the endpoints, and from -1 all the way to +infinity. So at this time, we're deciding what rules do we apply, and this is tricky. So we see a radical, so my mind goes, okay, I'm going to apply 2 or 3. And it's not in the denominator, so I'm looking at 2. But be careful, this nth root has to be even to apply 2 or 3. Because the nth root is 3, that means I'm not going to apply Rule 2. We don't have a variable in the denominator, so there's no rules that are going to be applied, which means all real numbers. You can write out the word all real numbers, or you could use this symbol. That means we are allowed to plug in any real number, and we'll have a corresponding output value. This is the trickiest example thus far, because we see all these variables and we see a radical. So let's just go one by one. First one, when I look at this radical, is the nth root even? So I eliminate the chance of applying rule 2 or rule 3. Now rule 1 is only applied if there is a variable in the denominator. Is there a variable in the denominator? Yeah, there's an x in the denominator, so I'm going to apply rule 1. This quantity cannot equal 0. X plus 4 cannot equal 0. What would happen if x was negative 4? Well, negative 4 plus 4 is 0. The cube root of 0 is 0, and we'd be in trouble because we can't have 0 in the denominator. So how do I represent this? It can be any number except for negative 4. So negative infinity all the way up to negative 4, and negative 4 all the way to positive infinity. First task in doing this problem is to decide, do any of the rules apply? So I see a radical, and I don't see a number. When we don't see a number, it's a hidden 2. So I know that rule 2 or 3 possibly will apply. This is in the numerator, so I'm going to apply rule 2. So I know this quantity has to be greater than or equal to 0. This goes back to what you learned in Unit 2 about solving inequalities. I'm going to find those hash marks by setting it equal to 0 and seeing, can I solve here by factoring? Yes, negative 2 times negative 3 multiplies to give me 6 and combines to give me negative 5. So x minus 2 and x minus 3. The leading coefficient is a 1. That doesn't change anything. And so I get an answer of 2 and an answer of 3. Those help me to identify the hashtags. Now what we learned last unit was that I'm going to put a closed dot at these positions, and then it's going to alternate yes, no, yes, or vice versa, no, yes, no. And wherever we see a yes, we highlight. So let's get started. What's the easiest value to test if it's not a hash mark?
0.
So I'm going to test this area over here because it has a 0. I'm going to test this area. So I'm going to plug in 0 and do some mental math. 0 squared is 0. Negative 5 times 0 is 0. Plus 6. I want to know, is this statement a true statement or a false statement? It's true. So this is a yes, no, yes. So what does that mean? It means I could plug in any value, including 2 to the left or including 3 to the right, into this function, and I would get a corresponding output value. It's part of the domain. So coming from negative infinity all the way up to 2, we include it, and we include 3 all the way to the right. I know I'm not going to apply rule 2 or rule 3. Why? Because there's no radical. So there's no chance of me applying rule 2 or rule 3. The only chance I apply rule 1 is if we have any variable in the denominator, which we do. So this portion cannot equal 0. So x squared minus 6x plus 5 cannot equal 0. So what multiplies to equal 5 and combines to give us negative 6? That would be negative 5 and negative 1. Is that correct? It is. X minus 5 and x minus 1. And so I'm finding those hash marks right now. I know it can't equal 0. It can't equal 0. So we get a 5 and a 1. So on my number line, I put it in order, 1 first, 5 second. It cannot equal those. Everything else, it can be a part of this. That represents the domain. Anything that's shaded, I could plug in for the value of x, and there would be a corresponding y value. How do I represent that? Negative infinity up to 1, don't include it. 1 to 5, don't include the endpoints. And 5 to positive infinity. Okay, so the last 3 examples in this video are tricky. Why? Because we're going to often apply more than one rule. We see a radical. The value here is the nth root is a 2. It's in the numerator, so I'm going to apply this rule. This portion has to be greater than 0. X minus 10 has to be greater than or equal to 0. Okay, what does that mean? It means x has to be greater than or equal to 10. And, by the way, rule 1, I see a variable in the denominator, so x minus 3 cannot equal 0. I need to apply both of these rules to a number line. So I make my number line, and I'm going to use a pencil at this point. I go to 10, and here's 3. And I find 10. I make a closed dot at 10, and I think of this as an arrow. I'm going to shade to the right. Now, this just says x can't equal 3. So if you wrote this for an assessment, it would be correct. When you look at your number line, they don't even include the 3, and the reason why is it just says 3 can't be a solution. Well, we can already see that, right? Because it's not part of this. So if I said to you, is 100 a possible value for the domain? The answer is yes. What about 11? What about 10? Yes. What about 0? Tricky one, what about 3? No. Okay. Why is this more difficult than the last one? So, again, we're going to apply rule number 2. I'm taking this portion, and I'm saying this portion here has to be greater than or equal to 0. And then this portion for rule 1 cannot equal 0. So, this goes back to what we learned in Unit 2 about graphing inequalities on a number line. So, I'm going to first start by finding those hash marks by setting it equal to 0, and I'm going to factor. This will factor into -4 and -1, so x minus 4 and x minus 1. So I have an answer of 4 and an answer of 1. So I'm going to start by that, and we need to put both of these concepts into one graph and then see where's they're overlapping. So here is 1 and here is 4. This tells me that I need to have a closed dot at those positions. And what's the easiest number to test? Okay, so here I'm going to test this area right over here. I'm going to test 0. And so I'm going to do it mentally. 0 squared, 0. -5 times 0, 0. Plus 4. Okay, so 0, 0 plus 4. Is this a true statement? I tested this, so this is going to be a yes, a no, and a yes. But now, hold on one second. I'm using a pencil. Okay, so I've done that part. I've taken care of this part. But now I need to apply the fact that x cannot equal -1. So I come back over here, identify where -1 is, I make an open circle. Turning to your partner, how would I represent this correctly in interval notation? Go. All right, so the rules here that apply, because the nth root is both even for both, would be, this would be rule 2. Now, what does rule 2 say? It says this has to be what? Greater than or equal to 0. And then this is rule 3, saying this portion has to be simply greater than 0. So I'm going to come out to, actually, I think I have enough room here to do this little bit here. We have 4x is greater than 8 divided by 4 divided by 4. So x is greater than 2. Okay, I will apply that later on. Then this portion, I'm going to make those hash marks. Okay, what multiplies equal -6 and combines to -5? -6 and +1. Do you guys agree? Now, a lot of you were rushing through your last test. You're trying to make these hash marks. And what mistake do you think a lot of kids made in this problem like this? They forgot to divide by the leading coefficient being 2. So 6 divided by 2 is 3, and 1/2 cannot be reduced. So I have a hash mark at 3 and a hash mark at -1/2. So I'm going to come over here. We're going to say this is -1/2, and we're going to say this is 3. I can see that I need to have an open circle, and now I'm going to test. Again, the easiest value to test is 0. 0 occurs right about here, so I'm going to test this area. I'm plugging in 0. 0 squared is 0 times 2 is 0. -5 times 0 is 0 minus 3. Is this a true statement? Is -3 greater than 0? No. I tested this as a no. That means this is a yes, and this is a yes. And now I have to apply this piece up here. So I find I find 2. I make a closed dot here, and I shade. And now I have to apply both rules. Both rules have to apply. It's almost as if your mom makes a rule and your dad makes a rule separately, and they're a little bit slightly different, and you're like, well, which rule do I have to apply? You have to apply the rules that both agreed upon. So do both of them, or are they both shaded over here? Do you see this part shaded over here? So I'm not going to include this. Do you see both shaded at this point? No. Here, do you guys see how this is the only part that has double shading? So I'm going to start here, and I have to make an open circle because there's an open circle below. And then I'm shading to the right. This is the only area that has double shading, right here and right here. And we're going to do an open circle because they both weren't closed. Like this is closed, but this was not. This would be my solution represented if we're not including 3, and then everything to the right.